Welcome students to the MOOC's series of lectures on non-parametric statistical inference. This is lecture number 9. As I said at the end of the last class that in this class we shall study association between two random variables. I hope all of you know how we study the association of two random variables in a parametric setup, and the corresponding measure is covariance. So, the situation is like this: given x and y, two random variables with a bivariate probability distribution. This is very important because if x and y are independent, then they do not have any covariance, that value is going to be 0. But if there is a joint distribution which we call bivariate probability distribution, then their covariance reflects the direction and amount of association or correspondence between the two random variables. So, we know that covariance of x y can be positive or negative, that is direction is plus or minus. If it is plus, implies that large values of x are associated with the large values of y, and similarly for small values. That is, small x is associated with a small y. On the other hand, if it is negative, then we know that if the covariance is negative, then large value of x is associated with small values of y. And similarly, large values of y are associated with small values of x, and it can be large or small depending upon how much spread is there for x and y, and in particular if x 1 y 1 x 2 y 2 x n y n is n pairs of observation, the covariance of x y is calculated using this following formula. It is 1 by n summation of I is equal to 1 to n x I minus x bar into y I minus y bar. Therefore, depending upon these magnitudes, the overall value of the covariance will be determined, and note that it is not unit free. That means that suppose x and y are height and weight of boys, then if height is measured in meters and weight is measured in kilograms, then these values will be smaller in comparison with when height is measured in foot and weight is measured in say pounds, and therefore, the magnitude of the covariance may change. Hence, a better measure comes in the form of correlation coefficient, which is unit free, and it is typically denoted by the symbol rho, and rho x y is defined as covariance of x y divided by sigma x sigma y, where sigma x and sigma y are the standard deviations for x and y. Note that the rho x y gives a measure of the linear relationship between x and y, and like covariance it can be plus or minus, but the maximum absolute value is 1. So, let me illustrate. Consider 5 points, that is n is equal to 5, and we have x 1, x 2, x 3, x 4 and x 5. We are checking its association with 3 other random variables y 1, y 2 and z. So, let us consider x and y 1, that means we are looking at these pairs of observations -2 -1, -1 0, 0 1, 1 2 and 2 3. Therefore, what is going to be the correlation between x and y 1? We look at this table, the mean of x is 0 and its variance is 2, the mean of y 1 is 1 and variance is 2. Therefore, rho x y 1 is sigma x I y I divided by n minus x bar times y bar whole divided by sigma x sigma y, and therefore, it is coming out to be -2 into -1, which is 2, -1 into 0, which is 0, 0 multiplied by 1, which is 0, 1 multiplied by 2, which is 2, and 2 multiplied by 3, which is 6, that divided by 5 minus x bar is equal to 0, y bar is equal to 1, and their standard deviations are √2, √2. Therefore, together we are getting the value is coming out to be 1, because 2 plus 2 is 4, 4 plus 6 is 10, 10 divided 5 is 2. Therefore, 2 divided by 2 is equal to 1. In a similar way, rho x y 2 coming out to be -1 and rho x z is coming out to be 0. Now, let us look into the data. We can see that they have the following relationship: y 1 is equal to x plus 1. That means, y and x has a positive relationship. As x increases, y 1 increases, as x decreases, y 1 decreases, and they are perfectly linear. Therefore, the correlation is coming out to be positive, and because it is perfectly linear, its value is 1. On the other hand, if we consider y 2, it is nothing but minus x plus 2. Therefore, for -2 it is coming out to be 4, for -1 it is coming out to be 3, and for 2 it is coming out to be 0. What is there in this data? Firstly, they are linear or linearly related, and secondly, if x increases, then y decreases. Because they are perfectly linear, the magnitude of the correlation is 1, but because increasing x means decreasing y, we get a negative sign there, that is, it is negatively correlated. That is very clear from this value. Now, if we consider the correlation of x and z, we can see that their relationship is z is equal to x square plus 1. Therefore, there is no linearity between them, and therefore, we can see that the correlation between them is 0. So, this is some intuition that we need to know when we talk about the association of two random variables. Therefore, let us recollect that the sign is positive or negative depending upon their mutual behavior, but it is independent of location change and unit change. It works well with normality assumption. As we said before, that the parametric statistical inference is based on a normality assumption. Therefore, the correlation coefficient that we discussed works well under normality assumption. However, the more the data deviates from normality, the more one finds the suitability of non-parametric methods for measuring association. That is, if the data is non-normal, then rather we should look at non-parametric way of measuring their associations. So, in this class we shall study two important non-parametric tests for association. One is called Kendall's tau and Spearman's rank correlation. So, let us first look into Kendall's tau. Often it is written like this from the Greek alphabet tau. So, what it is? It measures the association between x and y from a bivariate distribution based on n observations. So, let x 1 y 1, x 2 y 2 up to x n y n be the n pairs of observation taken from the bivariate distribution. They can be numeral, they can be ordinal, or they can be even rank data. Say for example, we are looking at marks of 4 students in 2 subjects. So, one way of looking at them is both of them are numeral. So, first student got 50 in one subject and 57 in the other subject, second student got 80.5 and 85, similarly 67.5 and 54.5 for the third student, and these two are for the fourth student. Again, one of them can be numeral, but the other can be say symbolic. Say many institutions they give grades instead of marks, and suppose the grades obtained by the 4 students in the second subject are C, A, D and B respectively. One can even represent the data using ranks. That means, with respect to the first subject, the ranks of the 4 students are 4th, 1st, 3rd and 2nd. As we can see that this is the highest one, this is the second highest one, this is the third highest and this is the fourth highest, and similarly the ranks for the second subject they are given below. Or the data can be something where one is rank, other one is symbolic. In short, we want to say that the data can be in many different forms, they need not be numeric, and therefore, in such cases the correlation coefficient that we discussed cannot be computed, because they need arithmetic manipulation of data with the help of the formula that we have given earlier. Then the question comes, how to measure their association. In Kendall's tau, it uses two notions, one is called concordance, other is called discordance, where concordance means agreement and discordance means disagreement. So, what does it mean? It means that the association is perfect for the ith and jth data point, namely x I y I and x j y j for all paired observations when I is not equal to j and I j is equal to from 1 to n. So, by definition, a relation is said to be in perfect concordance if for any two pairs x I y I and x j y j, whenever x I is less than x j, we also have y I is less than y j, or whenever x I is greater than x j, we also have y I is greater than y j. Together we can write that x I minus x j multiplied by y I minus y j is greater than 0. For example, consider the set of 5 observations x I y I is equal to 1 to 5, 1 3, 10 12, 8 7, 7 5, 14 and 18, then we can see that it shows perfect concordance. For example, if we consider these two pairs, here the first observation the value is increased and the second observation the value is also increased. Therefore, we are looking at 1 minus 10 multiplied by 3 minus 12, and we can see that this is going to be greater than 0. Similarly, we can check with respect to all the possible pairs, that is 5C too many pairs, and we can see that for all of them this value is coming out to be greater than 0, and therefore, this is a perfect concordance. At the same time, a relation is said to be perfect discordance if whenever xi is less than xj, we have yi is greater than yj. That is, if the value of x is increased, then value of y is decreased, or if value of x is decreased, then value of y is increased. In other words, these two together we can write as xi minus xj multiplied by yi minus yj has to be less than 0 for all ij. For example, let us choose arbitrarily these two pairs. Therefore, we get 2 minus 3 multiplied by 8 minus 6, and we know that this is coming out to be less than 0. The same one can compute with respect to all the 5C too many pairs. However, it is more natural that the paired observation does not exhibit perfect concordance or perfect discordance with respect to all the pairs. Again, for illustration, consider these 5 tuples. If we consider these two 11, 8 and 10, 12, we can see that value of x is decreased, but value of y is increased. Therefore, they are in discordance. However, if we consider these two pairs, the value of x is increased and value of y is also increased. Therefore, there is a concordance between these two pairs. Therefore, this sample does not show any perfect association, and that is very common. That is what in general we would expect, and therefore, we need to give a measure which resembles a degree of association between them. So, in Kendall's tau, these scores are given as follows. If it is perfectly concordant pair or they are in perfect concordance, then the value given will be +1. If perfect discordance, then value will be given -1. If neither of the above two criteria holds good, then both concordance and discordant measure will lie between +1 and -1. Thus, we can see a similarity with respect to correlation coefficient. It is desirable that increasing degree of concordance will be reflected by increasing positive values of tau. That means, the more is the degree of concordance, then the value of tau will go from 0 to 1. And similarly, increasing degree of discordance will be shown by the negative value as it is going from 0 to -1. But the main question is still there, how to score a set of paired observations. We understood what is going to be for perfect concordance or perfect discordance, but how to score in between? This answer comes from probability. So, let PC and PD denote the probabilities of perfect concordance and perfect discordance respectively for any two randomly chosen pairs I j. Now, this is to be calculated by taking into consideration all the NC too many pairs x I y I and x j y j, where I is not equal to j and they are running from 1 to n. Or in other words, what we are saying, we will consider all the NC too many pairs and we shall try to see how many of them are concordant and how many of them are discordant. So, from there we shall try to get a measure of the probability of concordance and discordance. So, given x 1 y 1, x 2 y 2 and x n y n, the tau value or Kendall's tau is probability of perfect concordance minus probability of perfect discordance, or in short we write tau is equal to P c minus P d, where P c is the probability of perfect concordance and P d is the probability of perfect discordance. Hence, tau is probability x I minus x j multiplied by y I minus y j is greater than 0 minus probability x I minus x j multiplied by y I minus y j less than 0. As we have already discussed that if these two pairs are discordant, then this product is going to be less than 0, and if they are concordant, then this product is going to be greater than 0, and this we are telling for an arbitrarily selected pair x I y I and x j y j. However, Kendall's tau has a basic assumption that we have seen with respect to most of our non-parametric tests, that the marginal distributions of x and y are going to be continuous. Now, what is P c? It is the probability of perfect concordance. Therefore, it is the probability that x I minus x j multiplied by y I minus y j is greater than 0. That means, it is the probability that x I is greater than x j and y I is greater than y j union x I is less than x j and y I is less than y j. That means, both of them will give positive or both of them will give us negative values, so that the product will remain positive. Since these two are disjoint events, we can write as probability x I greater than x j and y I greater than y j plus probability x I less than x j and y I less than y j. Now, this event x I greater than x j and y I greater than y j can be written as probability x I greater than x j minus probability x I greater than x j and y I less than y j. This is very straightforward and we can see it very easily from the Venn diagram. So, I am not going to explain that. You convince yourself that probability of this event can be written as the difference of these two probabilities, and in a very similar way probability x I less than x j and y I less than y j, this can be written as probability x I less than x j minus probability x I less than x j and y I greater than y j. Here it was less than, now it becomes greater than. Therefore, this whole thing can be written as probability x I greater than x j plus probability x I less than x j minus probability x I greater than x j and y I less than y j plus, because minus we have taken common, probability x I less than x j and y I greater than y j. Now, this part is equal to 1, because under continuity either x I is greater than x j or x I is less than x j, therefore, their sum is going to be 1, and this is nothing but the probability of discordance between x I y I and x j y j. Therefore, we can see that probability of concordance is equal to 1 minus probability of discordance. Therefore, the tau or Kendall's tau can be written as P c minus P d, which we have already defined, can also be written as 1 minus twice P d or twice P c minus 1. So, these are different formulae for computing Kendall's tau. So, let us first examine a few properties of tau. The value of tau is 0 if x and y are independent, because x and y are continuous and independent. Therefore, given I and j, probability x I greater than x j is same as x I is less than x j, and similarly probability y I is greater than y j is same as probability y I is less than y j. Therefore, probability of concordance is equal to probability x I greater than x j multiplied by probability y I greater than y j plus probability x I less than x j multiplied by probability y I is less than y j. Now, because of this equality, we can write this as probability y I less than y j, and similarly this as probability y I greater than y j. Therefore, we find that P c is same as probability x I greater than x j multiplied by y I less than y j plus probability x I less than x j multiplied by probability y I greater than y j, and we know that this entire thing gives us the probability of discordance. Therefore, if x and y are independent, probability of concordance is same as probability of discordance. Therefore, the value of tau is equal to P c minus P d is equal to 0. Therefore, if x and y are independent, the value of tau is 0. Let us examine some other properties of tau. Tau is symmetric with respect to x and y, that is tau of x y is equal to tau of y x, which is pretty obvious. I am not going to prove anything here, you can easily convince yourself. Tau x y is equal to tau of minus x minus y. This is again also very obvious, because we are considering the negative values of x and negative values of y. Therefore, the relative values, if x I greater than x j, will now change to minus x I is less than minus x j, and similarly y I greater than y j implies minus y I is less than minus y j. Therefore, when we are taking the product, whenever this was positive, then minus x I plus x j multiplied by minus y I plus y j will also be positive. Similarly, with respect to negative, therefore, tau of x y is equal to tau of minus x minus y, which is again by this observation is tau of minus y minus x. In a similar way, tau of x y is minus of tau of x minus y, or it is equal to minus of tau of y and minus x. Or in other words, the measure will be invariant under all transformations of x and y for which order of magnitude is preserved. Because we are not looking at the exact value, we are looking at whether it is positive or negative. Therefore, if the relative orders are preserved, then there is no change in the value of the Kendall's tau. Inferencing procedure. Suppose there is a sample x1, y1, x2, y2, xn, yn. The inferencing procedure needs to estimate the value of tau, that is to find point estimates for PC and PD, that is probability of concordance and probability of discordance. So, for each pair I j, when I is not equal to j, define A I j is equal to sine of x I minus x j multiplied by sine of y I minus y j, where sine is the sine function, that means it is plus 1 or minus 1, depending upon whether it is positive or negative. Then A I j can be defined as follows: it is 1 if the pair is concordant, it is minus 1 if the pair is discordant, and it is 0 otherwise. That means, when a pair is neither concordant nor discordant, and since it is a pair, it means that there will be some equality. Although under continuity assumption equalities should not happen, but in reality when we collect data, discrete data, there may be equalities. Therefore, we need to exclude those data points from further calculation. Therefore, the marginal probability distribution of A I j's is, it is P c if A I j is equal to 1. That means, probability that A I j will take a value 1, that probability is probability of concordance, that is P c. A I j will take a value minus 1, that probability is P d, and if A I j is equal to 0, that value is 1 minus P c minus P d. Therefore, expected value of A I j is equal to 1 times P c minus 1 times P d plus 0 times this quantity, which we can ignore, or in other words what we have is 1 times P c minus 1 times P d, which is equal to the value of tau. Therefore, this A I j helps us in estimating the value of tau. Now, if we take summation over A I j, the number of concordant pairs minus number of discordant pairs, that is what we are getting. If there is no ties, each pair will be either concordant or discordant, as I have mentioned. Therefore, the number of discordant pairs is going to be N c 2 minus the number of concordant pairs. Hence, an unbiased estimator for tau is provided by sigma over I and j, I j going from 1 to n and I less than j, A I j divided by N c 2, because there are N c 2 many possible pairs, which is coming out to be 2 times sigma sigma A I j upon n into n minus 1. So, this t value we compute from the sample, and it gives a measure of association between x and y. For illustration, consider these pairs 115, 612, 410, 88 and 69. Since there are 5 observations, therefore, we have 5 C 2, that means 10 pairs. So, let us consider this 10 pair 1 2 1 3 1 4 1 5 2 3 2 4 2 5 3 4 3 5 and 4 5. Now, we have to check how many of them are concordant, how many of them are discordant. So, we go pairwise. So, 1 and 15, as we can see that as 1, x values are 1 and 6 and 15 and 12. Therefore, this is a discordant pair. Therefore, the value of A I j is equal to minus 1. Similarly, you can calculate for all others. Let us just check the pair 2 and 3. It is 6 4 and 12 10. That means, as I go from second sample to the third sample, value of x is decreasing and value of y is decreasing. Therefore, that is a concordant pair, and therefore, as we see, we have got a plus 1 there. What is with respect to 2 and 5? Since the x values are 6, for both of them. Therefore, this pair is neither concordant nor discordant. Therefore, we get the value 0. So, similarly you can calculate for all other pairs. I am not going to do that, but now we have to see that we have to discard this pair because it is neither concordant nor discordant, and then we find that there is only one pair which are concordant and remaining 8 pairs they are all discordant. Therefore, probability of concordance is equal to 1 by 9, probability of discordance is equal to 8 by 9. Therefore, the computed value of tau from the sample is minus 7 by 9. So, that is the estimate of the Kendall's tau for this sample. Now, let us see a few things. Consider this pair 5 15, 8 14, 6 12 and 7 18. Therefore, we have the following pairs 4 C 2 which is 6, and in fact, we can see that 1 2 1 3 1 4, 2 3 2 4 and 3 4, and these are the values of aij's. Now, consider them with a different order. The same pair of observations, but we have permuted them differently. That means, the sample might have been taken in a different order, but what we see that the number of positive and number of negative, it still remains same. Or in other words, we can say that the distribution of aij does not change with permutation. That is an important property of Kendall's tau, that if we shuffle the data, that does not alter the value of the measure of association, that is tau. Let us consider another example. Again, we have taken this 4 pair of observation, we have computed this table of aij. Now, consider x values are replaced with their ranks. That means, if we look at this, the values are 5, 8, 6 and 7. So, suppose we rank them as 1, 2, 3 and 4, then now my data is transformed into this. Therefore, again if we calculate aij, we find that there is no change in the computation of aij between these two set of data. So, what does it tell us? It tells us that the distribution of aij does not change with the values replaced by ranks. What is the advantage? The advantage is that instead of numeric value, if we had A, B, C, etc., and they can be ordered perfectly, then there is no change in the value of the measure of association, namely Kendall's tau. So, generally we want to test if x and y are independent versus x and y are not independent. So, what we try to do? We try to compute the value of the t and we reject h naught if t is large. That means, the sample observation need not give us the exact value 0, but the measure of t should be less than some critical value C alpha, where C alpha is the critical value for level of significance is equal to alpha. That is what we are saying, under H naught tau is equal to 0, since the distribution is symmetric. Hence, reject H naught at level alpha if the observed value of tau satisfies that modulus of tau is greater than T alpha by 2. For small values of n, the null distribution of course can be directly evaluated, and the way we have done many problems through complete enumeration. we can also do that when the value of n is small. Now, let me give you another illustration. To make the calculation simple, we arrange the x observations in sorted order. So, we have arbitrary pairs x 1 y 1, x 2 y 2 up to x n y n. Suppose we convert them to ranks, therefore, what we get rank of x 1 y 1. Let me write it down for you, changing x I to its rank, we get R 1 y 1, R 2 y 2, R n y n, and if R 1 is less than R 2, less than R 3, less than R n, then this gives us of the form 1 y 1, 2 y 2, n y n, where 1 is the rank of x 1, 2 is the rank of x 2 and n is the rank of x n, or in other words, the calculation becomes simple if we arrange one observation, maybe the x in sorted order. Now, we have 3 pairs of observation. Let us sort x in increasing order 1, 2, 3, and then for y we can have all the 6 possible permutations 1, 2, 3, 1, 3, 2, 2, 1, 3, etc. And then we can compute the tau with respect to each permutation. And we will find that for this it is coming out to be 1 because they are perfectly concordant. For this order 3 to 1 there is perfect discordant, and for others we shall get the values like this. Thus, for relatively small values of n, the null distribution of the statistic t can be easily evaluated because we are getting the probability distribution of t. Let us now consider the other metric, that is Spearman's rank correlation, which also measures the association between two random variables which are jointly distributed. So, the measure of Pearson's correlation typically used for bivariate normal population cannot be used for other types of data directly. That is what we started with, that when we are computing the correlation which is called Pearson correlation, it can be used for normal population, but if the data is not of that type, then we can use a subtle variation of that which is called rank correlation. So, in this approach a pair x I y I is replaced by the ranks R I S I, where R I is the rank of x I among the x observations and S I is the rank of y I among the y observations. We have already seen how we can replace a value with its rank. So, we are not elaborating it much further. Suppose we have the 5 S's graded by 2 different examiners, one has given numerical scores, others have given grades, and we want to see to what extent the examiners agree with each other, or in other words the association between their evaluations. So, we can see that the distributions are not normal and there are values which are not numeric, and also we can see that they are not having the similar opinion with respect to the 5 S's, or in other words there is a disagreement between the two examiners. Hence, the question of measuring their association is important. Here we invoke our earlier definition of rho x y, which we have already defined. So, I am not going into the detail here, but for Spearman rank correlation the x I will be replaced by R I and yi will be replaced by Si, and therefore, from here we get the following. So, these are the ranks among the x's and these are the ranks among the y's, which is the scores given by examiner 2. Therefore, effectively by taking ranks, we convert the data into numeric, and this enables us to compute the correlation coefficient between R and S, which will now be of this formula, and this is called rank correlation. It of course has certain disadvantage, because we are losing a lot of information, but it has certain advantages, because it is easy to apply. Why it is easy to apply? Because of the simple thing that R takes values 1, 2, 3 up to n. Therefore, mean of R value is going to be n plus 1 by 2. Similarly, the mean of S is also going to be n plus 1 by 2. What about the variance? The variance is coming out to be n into n square minus 1 by 12, because it is very simple, because variance of R is equal to sigma over R I minus R bar whole square. Also we can write it as sigma R I square minus n times R bar square, that is the alternative formula for variance. Now, if we simplify them, we find that the variance of R is equal to n into n square minus 1 by 12. In a very similar way, variance of S is equal to n into n square minus 1 by 12. Therefore, when we put these values in the formula for rank correlation, what we get it? Sigma R I minus R bar into S I minus S bar summation over I is equal to 1 to n divided by their standard deviations. Now, because these two values are same, we get n cube minus n, and what we are getting eventually is this formula 12 upon n into n square minus 1 multiplied by, as we open up this product with the summation, we get sigma R I S I minus R bar into sigma S I minus S bar into sigma R I plus n times R bar into S bar, which is coming out to be 12 into sigma R I S I minus n R bar S bar divided by n into n square minus 1, which can be further simplified to 12 into sigma R I S I upon n into n square minus 1 minus 3 times n plus 1 upon n minus 1. Therefore, consider the problem that we are dealing with. We have the ranks of R's like this and the ranks S like this. Therefore, the rank correlation is coming out to be 12 times 1 into 2, that is 2, 2 into 1, that is 2, 3 into 4, that is 12, 4 into 5, that is 20, and 5 into 3, that is 15, divided by 5 into 5 square minus 1 minus 3 into 5 plus 1 divided by 5 minus 1, which is coming out to be 0.6. So, that is the rank correlation or Spearman's rank correlation between these two pairs of observation. Now, there is a alternative formula for that one. This is computed using the value of di, which is the difference in ranks for Ri and Si. So, di we can write it as Ri minus R bar minus Si minus S bar, because R bar is same as S bar, both are n plus 1 by 2. Therefore, summation of di square is equal to summation of square of these quantities, which we can open up and we get sigma R I minus R bar whole square plus S I minus S bar whole square minus 2 into R I minus R bar into S I minus S bar. Now, this is giving you the notion of the variance, and two of them, that is why we get 2 into n square minus 1 by 12 minus 2 into sigma r I minus r bar into S I minus S bar. Therefore, sigma 2 into sigma r I minus r bar into S I minus S bar, we can write it as 2 star n into n square minus 1 by 12 minus summation over d I square, or if we multiply this by 6, we get 12 into sigma r I minus r bar into S I minus S bar is equal to n into n square minus 1 minus 6 into sigma d I square. Since we have already seen that the rank correlation is equal to 12 into r I minus r bar into S I minus S bar divided by n cube minus 1. Therefore, together we can write that the rank correlation is equal to 1 minus 6 times summation d I square upon n into n square minus 1. Therefore, if we apply the same formula for the same data, then we get d I is equal to minus 1 plus 1 minus 1 minus 1 and plus 2. Therefore, 1 minus 6 into sigma d I square is coming out to be 1 minus 6 into 1 plus 1 plus 1 plus 1 plus 4 divided by n into n square minus 1, which is 5 into 24, that is 120. Therefore, again we get the same value 0.6. So, that is how we calculate the Spearman's rank correlation for a given set of paired observations. Again, we do the similar type of testing, whether x and y are independent or they are not independent. Therefore, we reject the null hypothesis if the absolute value of the rank coefficient is somewhat large, that is, it is greater than some threshold. Otherwise, we are going to accept that they are independent. We now consider an example to illustrate how we can test the null hypothesis H naught using the two measures of association, that is Kendall's tau and Spearman's rank correlation. So, consider the following random sample of 6 pairs from a bivariate population of random variables x and y. So, the values are 17.81 and y is equal to 20.48. Second sample is x is 20.19 and y is 18.13, like that. This is the sixth sample, x is 19 and y is 19.50. So, the task is that to use Kendall's tau and Spearman's rank correlation to test if the two variables are independent, and the alternative is that these two are not independent. So, let us first discuss Kendall's tau. We need to count the number of concordant pairs. So, for that we first arrange the pairs in increasing order of x. So, you can see that 15.56, 17.81, like that up to 22.55, and y's are kept accordingly as per the pairs. Now, we count the number of times y j minus y I is greater than 0, because we always know that if j is greater than I, then x j is greater than x I. So, we are looking at y j is greater than y I for 1 less than equal to I less than j less than equal to 6. Now, there are 62, that is 15 pairs to be considered, and we can see that the number of concordant pairs is 6. How? So, we look at, for the first one y is 18.50, there are 1, 2 and 3 of them are bigger than this value. Therefore, corresponding to the first pair we get the value 3. For the second pair it is 20.48 the value of y, but none of the other ones is greater than that. Therefore, we get 0. In a similar way, we get 1 for this one, namely from here, 1 for 18.13 and 1 for 17.79. So, the number of concordant pairs is 6. Since there are no ties in the y values, the number of discordant pair is going to be 15 minus 6, that is 9. Therefore, the observed value of T statistic, which is probability of concordance minus probability of discordance, which is coming out to be 6 minus 9 divided by 62, that is 15, and this gives us minus 0.20. Therefore, observed value of the T, which is the absolute value of the PC minus PD, is coming out to be 0.2. So, that is the statistic that we have to use for acceptance or rejection of the null hypothesis. Therefore, what we do? We check it with the tabulated critical value. So, we have taken the table from this side, I have given you for your benefit, and we get the following. So, this is the sample from the table, where corresponding to different ends, I am showing from 4 to 20 and different values of alpha 0.1, 0.05, 0.025 etcetera up to 0.001, we have been given the critical value. So, for our example, n is equal to 6. Therefore, when alpha is equal to 0.05, alpha by 2 is 0.025. Therefore, the critical value that we can see is 0.867. Again, if we look at 1% level of significance, then alpha is equal to 0.01. Therefore, alpha by 2 is equal to 0.005, and the corresponding value given here is 1. Now, our test statistic is 0.2, which is less than 0.867, and therefore, naturally less than 1. Therefore, we cannot reject the null hypothesis for alpha is equal to 0.05 and alpha is equal to 0.01. Now, let us solve the same problem using Spearman's rank correlation. So, we have already sorted the x values in ascending order, and let us determine the rank for the y values. So, let us focus on this table. X is in increasing order. Therefore, the rank of the elements are R 1 is equal to 1, R 2 is equal to 2, up to R 6 is equal to 6. Now, these are the corresponding y values, and let us see what are their ranks. So, this is rank 1, that is S 5 is equal to 1, S 4 is equal to 2, S 1 is equal to 3, S 3 is equal to 4, and x 6 is equal to 5, and x 2 is equal to 6. Therefore, what we get? R I minus S I is equal to minus 2, minus 4, minus 1, 2, 4 and 1. Therefore, as we know, we compute sigma d I square, which is coming out to be 42, and therefore, the value of R is equal to 1 minus 6 times 42 divided by 6 star 35, that is 1 minus 42 divided by 35 is equal to minus 0.2. Therefore, the test statistic R is also 0.2, because we take the absolute value of this. Again, as before, we look at the corresponding table. Again, I have given you the link for the table, and as before we look at for 0.025 and 0.005, the values that we can see corresponding to n is equal to 6 are 0.886 and 1, and therefore, since the observed value is less than 0.886, we cannot reject the H naught for alpha is equal to 0.05 and alpha is equal to 0.01. So, that is how we use the Kendall's tau or Spearman's rank correlation to test hypothesis about whether the sample pairs are showing independence or not. Large number approximations. As usual, when n is slightly large, we can try to approximate that using standard normal distribution. With respect to Kendall's tau, what we find that if t is the observed value of the statistic, then 3 times root over n into n minus 1 divided by square root of 2 into 2n plus 5, this whole multiplied by t may be considered as a standard normal distribution. We are not going to derive this thing, let us accept that, and the null hypothesis will be accepted or rejected by using z test with this value of z, that is obtained by a transformation of the value that we got from the sample for the statistic t. With respect to Spearman rank coefficient, under the null hypothesis, the random variable z is equal to r times root over n minus 1 has approximately a standard normal distribution, where r is the obtained value of the Spearman rank coefficient. However, it has been found that another statistic r times square root of n minus 2 divided by 1 minus r square approximately follows student's t distribution with n minus 2 degrees of freedom. And it has been found that for moderate values of n, that is n is not too large, then this t statistic gives a better result than the normal approximation. Okay friends, I stop here today. In the next class, I shall continue with some more discussions about different non-parametric tests. Thank you.